So you go back to that equation that we used summing the torques for friction, and we're like, oh, okay, force friction equals I alpha over R. We're like, yeah, but that alpha is just A over R, and that A, that's the linear acceleration down the ramp in the x direction. You're like, okay, so you have IA over R squared, and so that force friction just equals that right there. And one little note, remember it's the moment of inertia of a hoop, so you can also get rid of that right now. You could plug in mr squared to get rid of the moment of inertia of the hoop, and then you do that, the force of friction simplifies down nicely. You just plug in the mr squared for that, and it simplifies down to max, which is actually kind of cool. You know, if you're just doing physics for fun on the weekends, that's kind of cool how this simplifies down. Take your time. But if you're trying to pass the AP test and to go quickly, I know it's not always the best to go quickly, but if you're trying to get it done in a certain amount of time, it'd probably be the best to use energy, and we'll finish with that. So here's the deal. You know that the force of friction equals max. So now you're going to say, okay, we did a lot of work. We go back to our equation 1 from forces in the x. We say, we know that. The angle, they'll tell us the m great gravity is what it is going to be if we're on Earth or on the moon or whatever. But that FF that we just worked really hard to get, we found out FF equals mass times acceleration in the x. So you're going to say, all right, let's make a little substitution. We're going back to that very first equation. We're saying, let's get the force friction out of there. We'll plug in what we know. And you get this right here. mg sine of theta minus max equals that. You're like, whoa, our whole goal, remember, we got to get A, so we go back to kinematics land. We're going to add this over. You're going to get, oh, sorry, I got rid of my m's. Every term had an m, and then we're going to get something like that, and then we're going to add that over, and you get 2ax equals g sine of theta. You divide by 2, and you finally figure out the acceleration of this is g sine theta over 2. You're like, that makes me feel good. I got A. I have to finish. I'm going to use kinematics. Go back to your favorite kinematics equation. Let's say it started from rest. You know it went down the ramp at distance delta x. You're like, okay, started from rest. We know acceleration, call it delta x. And you get something like this. And you're like, I'm almost done. You can tell this method takes forever. And you're like, and delta x, if you want to get in terms of the height of the ramp or whatever, you can do a little substitution. You could say, hey, you know, the sine of theta is opposite over a hypotenuse right there. So you know delta x is going to work out sine theta equals h over delta x. And you could say, hey, so that means delta x is h over sine theta. And you do that. And after all that work, you figure out the final velocity is square root of gh. And I went kind of quick at the end, but that is, I want to show you that's a lot of work. I wouldn't do that. What I would do, I use the energy method. And so, but if you want to recap that, we summed our forces in the x, we summed our forces in the y. This wasn't super helpful because it made us have another unknown. So we said, let's look at torques. We looked at torques. We said, hey, that gets us alpha in there. And then we said, well, we know alpha equals A over R. We made a little substitution. But I'll say, go back and watch that if you want to. It's a good skill to know how to use. If you only learned 1 or 2 things from this really tough example, I would say, hey, make sure you know the force of friction is causing this wheel to rotate or this hoop to rotate. Gravity is a central force. Normal force is acting along the radius right there, so those are not causing the torque, okay? The force of friction is because it's acting 90 degrees relative to the radius right there. It's acting 90 degrees relative to that, okay? So go back and watch that if you want, but I'm going to finish by talking about the way I'd like you to do a question like this that I think is going to be a lot easier. All right, so we just spent a really long time talking about how to do this question to figure out how fast it's going at the end right here. We figured out finally that the velocity is the square root of g times h. So if you know gravity and you know how high the wheel starts from, you know it's going to be going square root of gh at the bottom. Energy is going to be a lot more friendly. So this wheel is hanging out there at the top. At the top, it's up in there, it's not moving at all. And we know that when something's up in the air, it's got a height, it's got potential energy, PE. All right, and as this wheel rolls, let's say first off, let's say the wheel didn't roll, it started zooming down the hill just like a block. Well, all that P would convert over to translational kinetic energy 1/2 mv squared. You're used to doing questions like that. 1/2 PE mgh goes over to 1/2 mv squared. But you know, you've rolled things down hills before. You know, not only do they move in a translational fashion from point A to point B, so they don't just go like this. I mean, it smeared my ink right there. They go down the hill, but they also roll. And if you want to picture it like this, it's kind of like, say you're in your office chair and you said, I'm going to push myself across the room. Well, if you just push yourself across the room, that's translational kinetic energy, right? And let's say case 2, you're in your office chair and you're just going to spin around. You're not going to go anywhere, you're just going to spin. That's rotational kinetic energy. But in the case of the wheel, you're going to be translating from point A to point B, so you're going to have the 1/2 mv squared, but you're also going to be turning at the same time. So that's like you in your office chair going across the room, pushing yourself at the same time as spinning yourself around. You're going to have the 1/2 mv squared energy, plus the rotational kinetic energy, which is 1/2 I omega squared. And if you haven't seen this yet, KE translational is what you're used to as 1/2 mv squared. We've been using that a ton. KE rotational, KE rot, you'll see it written kind of funny. The 1/2 comes along for the ride. M's become I's because it's rotational stuff, so moment of inertia. V's become omegas, it's still squared. So this is the formula for the translational kinetic energy that you're used to when you're just moving from point A to point B, all right? And this is the rotational energy that the object has as well. Another way to think about this, if you've ever thrown a baseball before, a baseball, when it moves from the pitcher's hand to the catcher's glove, it has translational kinetic energy because the ball is going from point A to point B. It's covering so many meters in a certain amount of time. But it also has rotational kinetic energy. So it's also spinning. So that also has two types of energy. In baseball, there's something called the knuckleball, where if you throw it, it has no spin. Well, the goal is to have no spin. So that would just have translational kinetic energy. But don't worry about baseball. Let's do this question right now. And watch how much faster it is. So you're going to PU converts over to KE. And we made an assumption. We're going to assume energy is conserved, but there's just enough friction to get it to roll. So it gets it to roll. There's a torque right there. And it's just still causing it to roll, but it's not consuming a large amount of energy of our system. So we're going to say EF minus EI equals, oops, I meant to draw this arrow over here. Boom, just like that. So EF, you're going to have the translational kinetic energy 1/2 mv squared that you're used to. But you're also going to have the rotational energy because that hoop is rotating down the ramp. So one little thing, if you had the block example and it just slid down the ramp, that block would be going faster at the very end because its energy goes from PE over to KE, translational. In the case of the hoop, it has to split that potential energy between the translational energy and the rotational kinetic energy. The only new thing we're adding here is this extra term because you're rotating now. And then you're like, okay, but I know the moment of inertia of a hoop. They said from the get-go it's mr squared. And one little thing, sometimes just like when we had A's and alphas over here, we have V's and omegas, and you gotta get them speaking on the same terms. So we're like, hey, let's go back. We know that V equals R omega, and we're like, we're just gonna make a substitution. We're gonna get the omega out of there and just substitute in V over R, just so they're speaking in terms of V's then. We're at this step right here. If you wrote this in the AP test, the AP graders would be like, the students know the potential energy converts over to translational kinetic plus the rotational kinetic energy because it's moving down and it's spinning at the same time. All right, so we have that, and then we're just subbing stuff in. Mr squared is the moment of inertia of a hoop. We got omega equals V over R. We're going to substitute that, and it kind of works out pretty slick because all of a sudden 1/2 mv final squared, 1/2, there's your moment of inertia of the hoop. There's your V over R, that's omega squared, and it is final. We're talking about the very end right there. And then minus mgh. They all have m's that go bye-bye, right? Divide through by an m, it's equal to 0. And then that is R squared. That's R squared on top, so those R squareds are going to go away. So you're going to get a 1/2 VF squared plus a 1/2 VF squared. You get something like this. That's pretty nice. A half plus a half gives you a whole. Minus GH. Add that over to that side, take the square root, and you figure out the velocity final of that hoop is square root of GH. Quite a bit easier than doing the forces, the torques, substitutions. We had a substitution. We had to get the omega out of there and get in terms of V. That wasn't terrible though. Okay, that was actually using the same information. Remember that came from S equals R theta, V equals R omega, A equals R alpha. Well, we got to use that just on one small step of the last question, and that's about the toughest thing we got to do here is we got to get the omega equals V over R step and get the omegas out of there. So I will say if you ever get some rolling on a ramp, yeah, they might make you draw a free body diagram, and that's okay. But you don't necessarily always have to use forces and torques to solve it. You can use your energy techniques, and that's an okay thing to have in your toolbox. Okay? Just because a tool is there doesn't mean you have to use it. One time I didn't have a hammer, and so I used the end of a screwdriver to go tap, tap, tap on a nail, and I think I chipped the end of my screwdriver. Yeah, I got the nail in, but I'll say that would be like you trying to force the issue and do the really hard method when, yeah, it'll work, but it's going to take you some time. But this way is just a little bit quicker and straight to the point. Okay? So thanks for watching. The only extra step is we had our PE converted over to KE translational plus the rotational. Something to notice, back in the day, when we did the block example, we'd have like square root of 2gh, velocity square root of 2gh, right? Well, now with hoops, it's just the velocity is the square root of gh, so that hoop's not going to be going quite as fast as the block was by the time it gets down the ramp. You can picture, if you only have so much PE, before it all went to KE, right? That's great. But now, KE translational, I should say. But now that same amount of PE is going to go to KE translational plus KE rotational. The KE translational part's not going to be quite as great. So it's not going to have as great a velocity for a hoop or a disc and things like that compared to a block. Okay? Thanks for watching.